What if I told you that in less than a blink of an eye, the entire universe expanded faster than the speed of light? This isn't science fiction, it's cosmic inflation, one of the most mind-bending ideas in modern cosmology. During the earliest moments of existence, the universe didn't just grow, it exploded outward in a fraction of a second, stretching space itself to unimaginable scales. But why does this matter? Cosmic inflation isn't just a wild theory, it's the foundation of how we understand the origins of everything, from galaxies to the very fabric of reality. And today, we're diving into 28 astonishing facts about this cosmic phenomenon that will completely reshape how you see the universe. From the echoes of the Big Bang still rippling through space to the clues hidden in ancient light, this journey will take you to the very edge of what we know and beyond. So buckle up, because what you're about to discover will leave you in awe of the sheer scale and mystery of the cosmos. Here's something that might blow your mind. During the very first moments of the universe, space itself expanded faster than the speed of light. That's right, this wasn't just a gentle stretch. It was an explosive, exponential growth spurt that happened in a fraction of a second. To put it into perspective, imagine blowing up a balloon to the size of the entire solar system in less time than it takes to blink. That's the kind of scale we're talking about. But here's the kicker: this expansion didn't involve objects moving through space faster than light. It was space itself stretching, and that changes everything. Normally, we think of the speed of light as the ultimate speed limit, but cosmic inflation bends the rules. It's like the universe hit the accelerator pedal, pushing the boundaries of what we thought was possible. This rapid expansion didn't just happen randomly, it set the stage for everything we see today. The galaxies, stars, and even the cosmic microwave background radiation. All of it traces back to this mind-boggling growth spurt, and while it sounds like something out of a sci-fi movie, it's grounded in real science. What's truly fascinating is that this expansion left behind fingerprints. Scientists have been piecing together clues from the faint afterglow of the Big Bang, known as the cosmic microwave background, to understand how this rapid stretching shaped the universe. These subtle ripples in space-time are like echoes from the very beginning, telling us a story about how everything came to be. And as we dig deeper, we're uncovering even more secrets about the universe's first moments. But that's just the start. There's so much more to unpack. Now, let's zoom in on something even more extraordinary: the seeds of galaxies themselves. During cosmic inflation, the universe wasn't just expanding. It was also filled with tiny quantum fluctuations, ripples in the fabric of spacetime so small they're almost impossible to comprehend. These fluctuations might seem insignificant, but they were the building blocks of everything we see in the cosmos today. Picture it like this: imagine sprinkling seeds in a garden. At first, they're scattered and barely noticeable, but over time, they grow into towering trees, sprawling plants, and vibrant flowers. In the same way, those tiny ripples in spacetime became the seeds for galaxies, stars, and even the massive clusters of matter that stretch across the universe. But how did something so small become so vast? It all comes down to the rapid expansion of space during inflation. As the universe stretched, these quantum fluctuations were stretched too, magnifying them into larger variations in density. Think of it like blowing up a balloon with tiny dots drawn on it. As the balloon expands, the dots grow farther apart and become more pronounced. Over billions of years, gravity took over, pulling matter together around these denser regions, forming the first stars, galaxies, and the intricate cosmic web we observe today. What's truly remarkable is that these ancient fluctuations aren't just a theoretical idea, they're still visible. Scientists have detected their faint imprint in the cosmic microwave background, the afterglow of the Big Bang. It's like finding an ancient map that shows where everything began. And here's the kicker: these fluctuations weren't random. They followed a pattern, a kind of cosmic blueprint that shaped the universe in a way that's both orderly and awe-inspiring. This brings us to the next mind-blowing fact. These quantum ripples aren't just relics of the past, they're still influencing the universe today. But more on that in a moment, because this story of cosmic seeds is just the beginning of understanding how the universe grew from a tiny speck to the vast, interconnected cosmos we call home. Now, let's turn our attention to one of the most extraordinary pieces of evidence for cosmic inflation: the cosmic microwave background, or CMB. Think of it as the universe's baby picture, a snapshot of what it looked like just 380,000 years after the Big Bang. This faint glow, barely detectable, is the afterglow of that explosive beginning, and it's been traveling through space for over 13 billion years to reach us. But it's not just a relic of the past, it's a treasure trove of clues about the universe's earliest moments, including the rapid expansion of cosmic inflation. What makes the CMB so special? It's not uniform. If you look closely, you'll find tiny variations in temperature, subtle differences that might seem insignificant but hold the key to understanding how the universe evolved. These variations, some as small as 1 part in 100,000, are like cosmic fingerprints, unique patterns left behind by the quantum fluctuations that occurred during inflation. Picture it like this: if the universe were a pond, inflation would have been the moment someone tossed a handful of pebbles into the water. The ripples that spread out aren't random. They carry information about the size, shape, and force of the pebbles. In the same way, the temperature variations in the CMB tell us about the tiny ripples in spacetime that existed during inflation. And here's the incredible part: these ripples didn't just disappear. They grew, stretched, and became the seeds for everything we see today. The denser regions in the CMB eventually collapsed under gravity, forming the first galaxies and stars, while the less dense regions became the vast cosmic voids we observe between them. It's like a cosmic blueprint, a map of how the universe went from a hot, dense soup of particles to the intricate web of galaxies and clusters we see today. But how do we even know this? Scientists have spent decades studying the CMB, using satellites like the Planck and WMAP missions to measure its temperature with incredible precision. These missions have mapped the CMB in stunning detail, revealing patterns that align perfectly with predictions made by the theory of cosmic inflation. It's as if the universe left us a message encoded in light, and we're finally learning how to read it. What's even more remarkable is how precise these measurements are. The patterns in the CMB aren't just random noise, they follow specific mathematical relationships that match what we'd expect from inflation. It's like finding a perfectly preserved fossil that tells us not just what happened, but how it happened. And this precision isn't just a lucky coincidence, it's a testament to how finely tuned the universe's early moments were. As we peel back the layers of this cosmic fossil, we're uncovering more than just the story of inflation. We're learning about the fundamental forces that shaped the universe, the seeds of structure that gave rise to galaxies, and the delicate balance that made life possible. And while the CMB might seem like ancient history, it's still guiding us today, offering new insights into the nature of the cosmos. But the story doesn't end here. These temperature variations aren't just relics of the past, they're also a window into the universe's future. And as we'll see next, the precision of these measurements is unlocking even deeper mysteries about the cosmos, revealing just how much we still have to learn. The precision of modern science is nothing short of breathtaking. Take the Planck satellite, for instance, a marvel of human ingenuity designed to map the cosmic microwave background with an accuracy that boggles the mind. Launched by the European Space Agency, Planck spent years collecting data, measuring the CMB's temperature variations down to a few millionths of a degree. These tiny fluctuations, barely perceptible, are the echoes of cosmic inflation, and they've been scrutinized with such care that they've become one of the strongest pieces of evidence for the theory. What makes these measurements so groundbreaking? It's not just the data itself, but what it tells us about the universe's earliest moments. The patterns in the CMB align almost perfectly with the predictions made by inflation theory. Think of it like solving a puzzle. The pieces fit so precisely that there's little room for doubt. The Planck satellite's findings have refined our understanding of the universe's expansion rate, the density of matter, and even the shape of spacetime itself. It's as if the universe handed us a detailed instruction manual, and we're finally learning how to read it. But this level of precision didn't come easily. Scientists spent years analyzing the data, sifting through noise, and cross-checking their results to ensure accuracy. The process is akin to listening for a whisper in a crowded room. Every detail matters, and even the smallest error could lead to the wrong conclusion. What they found was a universe that's remarkably smooth on large scales, but with just enough variation to explain the formation of galaxies and clusters. These findings didn't just confirm inflation, they deepened our understanding of how the universe evolved from a hot, dense state to the vast, structured cosmos we see today. And here's where it gets even more fascinating. These measurements have also helped us narrow down the possible models of inflation. Not all theories of cosmic inflation are created equal, and the Planck data have allowed scientists to test and refine these models, ruling out some and providing support for others. It's like having a set of keys and figuring out which one unlocks the door to the universe's origins. What's truly remarkable is how much we've learned from such a faint signal. The CMB is the oldest light in the universe, yet it's still teaching us new things about the cosmos. And as we continue to analyze these data, we're uncovering even more clues about the universe's beginnings, clues that might one day help us answer some of the biggest questions in science. But while precision measurements have given us a clearer picture of inflation, they've also sparked new questions. What powered this rapid expansion? What drove the universe to stretch so dramatically in such a short time? The answers lie in the mysterious energy behind inflation, a force so powerful it reshaped the entire cosmos. And that's where we're headed next, diving into the enigmatic energy that set the universe in motion. At the heart of cosmic inflation lies a mystery that has puzzled scientists for decades. What could possibly power such an explosive expansion? Enter the Inflaten field, a hypothetical energy field that acted like the cosmic engine behind this incredible event. Picture it as a kind of fuel, but instead of gasoline or electricity, this field was made up of energy so exotic and powerful that it stretched the fabric of space itself. For a brief moment, this field dominated the universe, driving its rapid expansion faster than the speed of light. But like any fuel, it didn't last forever. After a fraction of a second, the Inflaten field began to decay, releasing its energy in a colossal burst that kick-started the Big Bang as we know it. Think of it like this. Imagine a car engine revving at full throttle, pushing the vehicle to incredible speeds. The Inflaten field was that engine, accelerating the universe's growth at an unimaginable rate. But instead of burning fuel, it tapped into a reservoir of energy that we still don't fully understand. As the field decayed, its energy transformed into the particles and radiation that filled the early universe, setting the stage for everything that followed: stars, galaxies, and even us. This transition from inflation to the Big Bang wasn't just a cosmic coincidence. It was a carefully orchestrated process, one that shaped the destiny of the cosmos. What makes the Inflaten field so fascinating is how it challenges our understanding of physics. It's not something we can see or touch, but its effects are written across the universe. The rapid expansion it caused smoothed out the cosmos, making it nearly uniform on large scales, while the quantum ripples it left behind became the seeds for galaxies and clusters. And yet, despite its profound impact, the Inflaten field remains theoretical, a ghostly presence that scientists are still trying to pin down. This raises an intriguing question. If the Inflaten field decayed billions of years ago, how do we know it ever existed? The answer lies in the cosmic microwave background, the afterglow of the Big Bang. The patterns we see in this ancient light are like echoes of the Inflaten field's energy, offering clues about its properties and behavior. It's as if the universe left us a breadcrumb trail, leading us back to its very first moments. But the story of the Inflaten field doesn't end with its decay. Its legacy lives on in the structure of the universe, the distribution of galaxies, and even the fundamental forces that govern reality. And as we'll see next, this mysterious energy field didn't just shape the cosmos, it also set the stage for one of the most profound mysteries in modern physics, the nature of dark energy. The horizon problem is one of those cosmic mysteries that keeps scientists up at night. Here's the puzzle. When we look out into the universe, no matter which direction we point our telescopes, everything looks remarkably similar. The temperature of the cosmic microwave background, for example, is almost exactly the same everywhere, down to a few thousandths of a degree. But here's the catch. According to the standard Big Bang model, there hasn't been enough time for light or heat to travel between these distant regions of the universe. So how did they all end up so uniform? It's like walking into a room where every wall is painted the exact same shade of blue, even though no one ever mixed the paint together. This is where cosmic inflation comes to the rescue. Imagine the universe as a tiny drop of paint so small that all the particles within it are in constant contact, mixing and blending until they reach a perfectly uniform color. Now imagine that drop suddenly expanding to the size of an entire galaxy in less than a blink of an eye. During inflation, the universe wasn't just stretching, it was smoothing itself out, like stretching a piece of dough until every part of it becomes even and consistent. This rapid expansion allowed regions that were once close together to spread far apart while still retaining that uniformity. It's as if the universe hit a cosmic reset button, ensuring that every corner of it started from the same baseline. But how does this solve the horizon problem? Before inflation, the universe was small enough for all its parts to interact and reach thermal equilibrium, essentially, to even out their temperatures. Then, during inflation, those regions were stretched far beyond the distance light could have traveled in the time since the Big Bang. What we see today as distant, seemingly disconnected parts of the universe were once close neighbors sharing the same conditions. This explains why the cosmic microwave background looks so uniform in all directions. It's a snapshot of that early, well-mixed state. Think of it like two friends standing at opposite ends of a football field. If they start running away from each other at the same speed, they'll quickly lose sight of one another. But if the field itself suddenly expands, stretching the distance between them faster than they can run, they'll appear to be impossibly far apart, even though they were once standing side by side. That's essentially what happened during inflation. Distant regions of the universe were once close enough to exchange heat and energy, but inflation stretched them apart faster than light could keep up. This elegant solution not only explains the uniformity of the universe, but also highlights the power of cosmic inflation as a theory. It's like finding the missing piece of a jigsaw puzzle, one that fits so perfectly it transforms the entire picture. And while inflation answers the horizon problem, it also raises new questions like what triggered this rapid expansion in the first place. But that's a mystery for another time, because there's another cosmic puzzle waiting to be unraveled, one that takes us even deeper into the fabric of reality. Now let's tackle one of the most elegant solutions cosmic inflation offers: the flatness problem. When we say the universe is flat, we're not talking about its shape like a pancake. Instead, it's about the geometry of space itself, the way distances and angles behave on the largest scales. Imagine you're standing on an infinite plane, where parallel lines never meet and the angles of a triangle add up to exactly 180 degrees. That's the kind of flatness we're referring to, and it's a feature of our universe that has puzzled scientists for decades. Why is this flatness so puzzling? Well, according to the laws of physics, the universe has a natural tendency to curve over time. Think of it like rolling a ball down a hill. It's almost inevitable that it will curve or bend as it moves. But when we observe the cosmos, we find that space is astonishingly flat, almost perfectly so. This raises a critical question: how did the universe avoid curving, especially over billions of years of expansion? This is where cosmic inflation steps in as the ultimate cosmic straightener. During that brief but explosive period of rapid expansion, the universe was stretched so dramatically that any initial curvature was effectively ironed out. Picture it like taking a crumpled piece of paper and stretching it in all directions until it becomes perfectly smooth and flat. Inflation did something similar to space itself, smoothing out any bends or curves and leaving us with the remarkably flat universe we observe today. But why does this matter? A flat universe isn't just a neat quirk of geometry, it's a cornerstone of our understanding of the cosmos. It tells us about the balance of matter and energy in the universe, the rate of its expansion, and even its ultimate fate. A flat universe suggests that the total density of matter and energy is precisely balanced, like a tightrope walker perfectly poised between falling forward or backward. This delicate equilibrium is one of the key predictions of inflation, and it's been confirmed by countless observations, including the cosmic microwave background. And here's another fascinating layer: this flatness isn't just a lucky coincidence. Inflation doesn't just predict a flat universe, it demands it. The rapid expansion stretches space so thoroughly that it leaves no room for curvature, no matter how the universe started. It's like blowing up a balloon to an enormous size. No matter how wrinkled it was at the start, it becomes smooth and almost flat as it expands. This brings us to an even more profound idea. If inflation can produce a flat universe, could it also create multiple universes, each with its own geometry and laws of physics? The answer might lie in the multiverse theory, a concept that takes the implications of inflation to their ultimate extreme. But before we dive into that mind-bending possibility, let's take a moment to appreciate just how much inflation has already explained about the universe we call home. Now, let's venture into one of the most mind-expanding ideas in modern cosmology: the possibility that cosmic inflation didn't just create our universe, but an infinite number of others. This is the multiverse hypothesis, a concept that stretches the imagination and challenges everything we think we know about reality. If inflation didn't stop everywhere at once, if pockets of space continued to expand exponentially while others settled into stable universes like ours, then the cosmos could be teeming with countless bubble universes, each with its own unique set of physical laws. Picture it like a cosmic foam where each bubble represents a separate universe, some familiar, others wildly different, existing alongside ours in a vast, incomprehensible expanse. But how could this even happen? The key lies in something called eternal inflation, a process where inflation doesn't end uniformly across the universe. Instead, it slows down in some regions, creating stable universes like ours, while continuing to accelerate in others, birthing new bubbles endlessly. It's like a cosmic tree with infinite branches, each branch a universe with its own rules, its own stars, and perhaps even its own forms of life. In this scenario, our universe is just one leaf on an infinitely growing tree, surrounded by countless others we may never see or touch. Here's where it gets even more fascinating. If the multiverse exists, it could explain why our universe seems so finely tuned for life. In a landscape of infinite possibilities, there's bound to be at least one universe where the conditions are just right for stars, planets, and beings like us to exist. But does that mean we're alone in this vast cosmic ocean? Or are there other universes out there, each with its own version of reality, its own physics, and maybe even its own civilizations? It's a question that pushes the boundaries of science and philosophy, inviting us to rethink our place in the grand scheme of things. The multiverse isn't just a wild idea. It's a natural extension of the theory of cosmic inflation, one that offers answers to some of the deepest questions in physics. Why are the fundamental constants of nature so precise? Why does our universe have the exact properties needed for life? In a multiverse, these questions take on a new dimension, suggesting that what we see as fine-tuning might simply be the result of chance, a cosmic lottery where our universe was the winning ticket. And yet, for all its elegance, the multiverse remains a hypothesis, a tantalizing possibility that's still beyond our ability to test directly. But that doesn't mean it's purely speculative. The same mathematics that describe cosmic inflation also hint at the existence of these bubble universes, and while we may never see them, their fingerprints might still be hidden in the fabric of our own universe. Could the cosmic microwave background hold clues to their existence, or might gravitational waves, ripples in spacetime, carry echoes of other universes colliding with ours? These are the questions scientists are grappling with as they explore the edges of what we know. As we ponder the implications of a multiverse, it's worth remembering that every groundbreaking idea in science starts as a question, a spark of curiosity that leads us to new horizons. And while the multiverse may feel like science fiction, it's rooted in the same principles that have guided our understanding of the cosmos for decades, principles that continue to reveal the universe's deepest secrets. But before we dive deeper into the mysteries of inflation, let's take a closer look at the evidence that supports this extraordinary theory and how it's shaping our understanding of the universe's origins. Now, let's talk about something that could be the ultimate confirmation of cosmic inflation: primordial gravitational waves. These are ripples in the fabric of spacetime itself, created during the universe's explosive expansion. Think of them as echoes from the very first moments of existence, vibrating through the cosmos like the faintest whispers of a distant symphony. If we could detect these waves, it would be like finding the smoking gun of inflation, a direct signal from the universe's birth. But here's the catch: these ripples are incredibly subtle, so faint that detecting them is like trying to hear a single note in a roaring concert hall. So, why are these gravitational waves so important? They're not just any ripples, they're unique fingerprints left behind by the rapid stretching of space during inflation. Unlike the cosmic microwave background, which shows us the universe's baby picture, gravitational waves would give us a glimpse of its first cry, a snapshot of the moment inflation began. These waves carry information about the energy scale of inflation, the forces at play, and even the nature of spacetime itself. It's like having a cosmic time machine, allowing us to peer back to the very beginning of everything. Detecting these waves, however, is no small feat. Scientists have been searching for them for decades, using tools like ground-based observatories and space-based detectors. One of the most promising methods involves studying the polarization of the cosmic microwave background. Gravitational waves from inflation would have left a distinct pattern in this ancient light, a swirling imprint known as B-mode polarization. Finding this pattern would be like discovering a hidden message in a cosmic treasure map, pointing us directly to the origins of the universe, but the search is far from easy. The signals are incredibly weak, buried under layers of noise from other cosmic phenomena. It's like trying to hear a whisper in a crowded room. Every detail matters, and even the smallest interference can throw off the results. Despite these challenges, researchers remain hopeful. Projects like the BICEP and Keck Array telescopes in Antarctica, as well as future missions like the LIGHT-BIRD satellite, are pushing the boundaries of what we can detect. These efforts are driven by the tantalizing possibility that we might one day unlock the secrets of inflation and confirm one of the most profound theories in cosmology. What makes this search so exciting is the potential payoff. If we detect primordial gravitational waves, it wouldn't just confirm inflation, it would revolutionize our understanding of the universe. We'd gain new insights into the fundamental forces that shaped reality, the energy scales involved in the early universe, and even the nature of space-time itself. It's a quest that combines cutting-edge technology with the deepest questions in science, and it's one that could redefine our place in the cosmos. But as we'll see next, the challenges of detecting these waves are as immense as the rewards. From the precision required to isolate these faint signals to the technological innovations needed to push the boundaries of observation, the journey to uncover primordial gravitational waves is a story of persistence, ingenuity, and the relentless pursuit of knowledge. The search for primordial gravitational waves is one of the most ambitious scientific endeavors of our time, but it's also one of the most challenging. These ripples in space-time, generated during the universe's explosive expansion, are so faint that detecting them is like trying to hear a single drop of water fall in the middle of a thunderstorm. The signals are incredibly subtle, buried under layers of cosmic noise from other phenomena like cosmic rays, galactic dust, and even the Earth's own atmosphere. To make matters more complicated, the gravitational waves from inflation are billions of times weaker than those detected by observatories like LIGO, which famously confirmed the existence of gravitational waves from colliding black holes and neutron stars. So, how do scientists even begin to tackle such a monumental task? The answer lies in some of the most ingenious experiments ever devised. Take the BICEP project, for example. Located at the South Pole, one of the coldest and driest places on Earth, BICEP and its successor, the Keck Array, are designed to study the cosmic microwave background in unprecedented detail. These telescopes focus on a specific feature called B-mode polarization, a swirling pattern in the ancient light that could be the telltale signature of primordial gravitational waves. It's like searching for a faint, hidden watermark on a piece of paper that's been crumpled and smoothed out countless times. The precision required is mind-boggling, with instruments cooled to just a fraction of a degree above absolute zero to minimize interference. But even with such cutting-edge technology, the journey has been far from straightforward. In 2014, the BICEP team announced what they thought was a groundbreaking discovery: evidence of B-mode polarization that could point to gravitational waves from inflation. The excitement was palpable, but further analysis revealed that the signal might have been contaminated by galactic dust. It was a sobering reminder of just how difficult this search truly is. Yet, instead of being discouraged, scientists doubled down, refining their methods and developing new techniques to distinguish between cosmic signals and interference. This kind of perseverance is what drives the scientific process. Every setback is a lesson, and every challenge is an opportunity to innovate. Future missions like the LIGHT-BIRD satellite aim to take this search to the next level, scanning the skies from space to avoid atmospheric interference altogether. The stakes are high, but so are the potential rewards. Detecting primordial gravitational waves wouldn't just confirm cosmic inflation. It would open a new window into the universe's earliest moments, revealing details about the energy and forces that shaped reality itself. As we marvel at the ingenuity and determination behind these experiments, it's worth asking, What if inflation isn't the whole story? While it's the leading explanation for the universe's rapid expansion, there are alternative theories that offer their own intriguing possibilities. Some propose that the Big Bang wasn't the beginning but part of a cyclical process, while others suggest entirely new physics at play. Exploring these ideas takes us even deeper into the mysteries of the cosmos, challenging our understanding and pushing the boundaries of what we thought was possible. But that's a story for the next segment. What if cosmic inflation isn't the only explanation for the universe's origins? While it's the leading theory, it's not the only game in town. Some scientists have proposed alternative ideas that challenge our understanding of the Big Bang and the early universe. One such idea is the cyclic model, which suggests that the universe goes through endless cycles of expansion and contraction, a cosmic heartbeat, if you will. In this scenario, the Big Bang wasn't a singular event but just one phase in an infinite loop of creation and destruction. Picture it like a cosmic accordion, expanding and collapsing over and over, each cycle leaving behind traces of the previous one. It's a fascinating concept, but it raises questions. What triggers these cycles, and how do they leave the universe so smooth and flat, just as we observe today? Another intriguing alternative is the bouncing universe theory, which proposes that our universe is the result of a previous one collapsing and rebounding. Instead of a Big Bang, there was a big bounce, a moment when a contracting universe reached a critical density and sprang back into expansion. This idea avoids the singularity problem of the Big Bang, where the laws of physics break down, but it introduces its own challenges. What caused the bounce, and how does this theory account for the uniformity and flatness we see in the cosmos? These questions keep scientists debating, and while the bouncing universe model is compelling, it lacks the same level of observational support as inflation. Then there's the ekpyrotic model, which envisions our universe as the result of a collision between two higher dimensional branes, a concept borrowed from string theory. In this scenario, the Big Bang wasn't an explosion but a collision, like two sheets of paper slamming together, releasing energy and creating the universe as we know it. This idea is elegant in its own way, but it too struggles to explain the smoothness and flatness of the cosmos without invoking something akin to inflation. So, how do these alternatives stack up against cosmic inflation? While they offer creative solutions to some of the Big Bang's puzzles, none have the same breadth of evidence supporting them. The cosmic microwave background, the distribution of galaxies, and the flatness of the universe all align with inflation's predictions in remarkable detail. But that doesn't mean these other theories are without merit. They push us to think outside the box, challenging our assumptions and sparking new ideas about how the universe might work. What's truly exciting is that these alternative theories aren't just competing ideas, they're part of a larger conversation about the nature of reality. Each one offers a unique perspective, a different lens through which to view the cosmos. And while inflation remains the frontrunner, the exploration of alternatives keeps science dynamic and alive, reminding us that there's always more to discover. As we consider these possibilities, it's worth reflecting on what they mean for our understanding of existence. If the universe didn't begin with a single explosive event, but with cycles, bounces, or collisions, how does that change the way we see ourselves? These questions aren't just scientific, they're deeply philosophical, touching on the very nature of time, space, and our place in the grand scheme of things. And that's where we're headed next, diving into the profound implications of cosmic inflation and what it reveals about the universe and ourselves. Cosmic inflation doesn't just reshape our understanding of the universe, it challenges the very way we think about time, space, and existence itself. At its core, inflation raises profound philosophical questions that push the boundaries of human thought. Was there truly a beginning to the universe, or is our cosmos part of an infinite cycle, a single chapter in an eternal story? These aren't just scientific questions, they're deeply existential, forcing us to confront the limits of what we can know and understand. As physicist Stephen Hawking once remarked, the universe doesn't allow perfection. And yet, inflation seems to hint at a kind of cosmic perfection, a finely tuned process that set the stage for everything we see today. But what does that mean for our place in the grand scheme of things? One of the most striking implications of inflation is the idea that the universe might not have had a singular beginning. Instead, it could be part of a larger, perhaps infinite multiverse, a tapestry of universes, each with its own laws and history. This idea resonates with ancient philosophical concepts, like the Hindu notion of an eternal cycle of creation and destruction, or the Greek philosopher Heraclitus's belief that everything flows and nothing remains the same. Inflation, in a way, bridges the gap between ancient wisdom and modern science, inviting us to see the universe not as a static entity, but as a dynamic, ever-evolving process. But inflation also challenges our understanding of time. If the universe expanded faster than light during its earliest moments, what does that mean for the arrow of time? Does time even exist at the quantum level, or is it an emergent property of the universe's expansion? These questions aren't just abstract musings, they're central to how we interpret the cosmos. As philosopher Immanuel Kant once argued, time and space are the frameworks through which we perceive reality. But inflation suggests that these frameworks might be far more malleable than we ever imagined. And then there's the question of existence itself. If inflation created the seeds of galaxies and stars, does that mean the universe is inherently creative, constantly birthing new structures and possibilities? Or is it simply following the laws of physics, a cosmic machine playing out an inevitable script? These questions blur the line between science and philosophy, reminding us that the search for knowledge isn't just about finding answers, it's about asking better questions. As we grapple with these ideas, it's worth remembering that inflation isn't just a scientific theory, it's a lens through which we can explore the deepest mysteries of existence. And while it raises as many questions as it answers, that's precisely what makes it so fascinating. It invites us to look beyond the horizon of what we know, to imagine new possibilities and rethink our understanding of reality. But as we'll see next, this journey of discovery isn't just philosophical, it's deeply mathematical. The language of numbers and equations plays a crucial role in unlocking the secrets of cosmic inflation, revealing patterns and truths that words alone cannot express. Mathematics is the unsung hero behind the story of cosmic inflation. Without it, we'd be left staring at the night sky, marveling at its beauty but utterly clueless about its origins. Equations, numbers, and abstract symbols might seem dry at first glance, but they're the tools that allow us to decode the universe's deepest secrets. Take Einstein's theory of general relativity, for example, a masterpiece of mathematics that describes how gravity shapes the cosmos. It's the foundation upon which inflation theory is built, a framework that lets us explore how space can stretch, twist, and expand. But it's not just about gravity. Quantum field theory, with its intricate equations, steps in to explain the tiny ripples in spacetime that became the seeds of galaxies. Together, these mathematical tools form a cosmic Rosetta Stone, translating the language of the universe into something we can understand. Think of it like solving a jigsaw puzzle. Each equation is a piece, and when you fit them together, a picture begins to emerge. A picture of how the universe grew from a microscopic speck to the vast expanse we see today. But this isn't just any puzzle. It's one where the pieces are constantly shifting, revealing new details and connections. For instance, the equations of inflation predict how much the universe should have stretched, how smooth it should be, and even the patterns we'd expect to see in the cosmic microwave background. And when observations match those predictions, that's when the puzzle starts to make sense and the story of inflation comes alive. What's truly remarkable is how these mathematical models don't just describe the universe, they predict it. They allow us to peer back in time, billions of years before the first stars ignited, to a moment when the cosmos was a seething cauldron of energy and potential. It's like having a time machine built entirely out of numbers and symbols, one that takes us to the very edge of what's possible to know. But mathematics isn't just about solving equations, it's about asking the right questions. Why does the universe look the way it does? What drove its rapid expansion? These are the kinds of questions that keep physicists up at night, and it's mathematics that gives them the tools to find answers. And as we'll see next, those answers aren't just theoretical. They're grounded in real-world observations made possible by some of the most advanced technology humanity has ever created. Because while mathematics might be the language of inflation, it's technology that lets us listen to the universe speaking it. Behind every groundbreaking discovery about cosmic inflation lies a hidden hero: technology. From the cold, desolate plains of Antarctica to the silent vacuum of space, advanced instruments have become our eyes and ears, peering into the universe's earliest moments with astonishing precision. Take, for example, the Planck satellite, a marvel of engineering that mapped the cosmic microwave background in exquisite detail. Launched by the European Space Agency, Planck spent years scanning the skies, measuring temperature variations down to a few millionths of a degree. These tiny fluctuations, barely perceptible, are the echoes of inflation, and they've been scrutinized with such care that they've become one of the strongest pieces of evidence for the theory. Without these technological marvels, we'd be left guessing about the universe's origins, relying on speculation rather than hard data. But it's not just space telescopes that are pushing the boundaries of cosmology. On the ground, supercomputers are crunching mind-boggling amounts of data, simulating the universe's evolution with unprecedented accuracy. These digital laboratories allow scientists to test theories of inflation, modeling how quantum fluctuations grew into galaxies and clusters over billions of years. It's like having a cosmic time machine at our fingertips, one that lets us rewind the universe's history and see how it all began. And the pace of discovery is accelerating. Every year brings new breakthroughs, from the detection of gravitational waves to the refinement of cosmological models. One of the most exciting developments in recent years is the BICEP and Keck array experiments, located at the South Pole. These telescopes are designed to detect the faintest signals in the cosmic microwave background, specifically the swirling patterns known as B-mode polarization. These patterns, if found, could be the smoking gun of inflation, a direct signal from the universe's explosive expansion. While the search has been challenging, with initial signals potentially contaminated by galactic dust, the technology behind these experiments continues to improve. Future missions like the LightBird satellite aim to take this search to the next level, scanning the skies from space to avoid atmospheric interference altogether. The synergy between technology and cosmology is a testament to human ingenuity. Each new instrument, each leap in computational power, brings us closer to understanding the universe's origins. But technology doesn't work alone. It's the result of collaboration, of scientists and engineers working together across disciplines and borders. And that's where our next fact comes in, exploring how teamwork and shared knowledge are driving some of the most exciting discoveries in cosmology. Cosmology isn't just the work of a few brilliant minds. It's a global effort, a symphony of collaboration that spans continents, cultures, and disciplines. Scientists from every corner of the world come together, pooling their expertise and resources to unlock the secrets of cosmic inflation. Take the Planck mission, for example. This groundbreaking project, led by the European Space Agency, involved researchers from over 40 countries, all working in unison to map the cosmic microwave background with unparalleled precision. The data they collected didn't just belong to one team or nation, it became a shared treasure, a foundation for discoveries that have reshaped our understanding of the universe. But Planck is just one piece of the puzzle. The James Webb Space Telescope, a marvel of international engineering, is another shining example of global collaboration. With contributions from NASA, the European Space Agency, and the Canadian Space Agency, Webb is designed to peer deeper into the cosmos than ever before, capturing light from the earliest galaxies and shedding new light on the aftermath of inflation. These projects aren't just about building telescopes or launching satellites, they're about bringing together the best minds, the brightest ideas, and the most advanced technology to answer questions that no single nation could tackle alone. What makes this global effort so powerful is the diversity of perspectives it brings. Scientists from different backgrounds and disciplines approach the same problem from unique angles, sparking new ideas and uncovering connections that might otherwise go unnoticed. It's like solving a jigsaw puzzle with a team. Each person brings a different piece, and together they create a picture far greater than the sum of its parts. And it's not just about the big missions. Everyday collaboration happens in labs, universities, and conferences, where researchers share data, debate theories, and push each other to think bigger and dig deeper. This spirit of teamwork is what drives scientific progress forward. Without it, we'd be limited to isolated pockets of knowledge, each one incomplete on its own. But by working together, scientists have been able to piece together a story that spans billions of years. A story that began with the explosive expansion of cosmic inflation and continues to unfold with every new discovery. And as we look to the future, this global effort will only grow more important as we tackle even bigger questions about the nature of the universe. But how did we get here? How did the theory of cosmic inflation go from a bold idea to one of the most profound explanations of our universe's origins? That's where we're headed next, diving into the history of inflation theory and the brilliant minds who brought it to life. The story of cosmic inflation isn't just about the universe, it's also about the brilliant minds who dared to imagine how it all began. The theory didn't spring fully formed into existence. It evolved over decades, shaped by curiosity, debate, and a relentless pursuit of understanding. It all started in the late 1970s when physicist Alan Guth had a eureka, a moment while working on a seemingly unrelated problem in particle physics. He realized that the early universe could have undergone a rapid, exponential expansion, a flash of insight that would forever change our understanding of cosmology. Guth called this process inflation, and with that, a new chapter in science began. But like any groundbreaking idea, inflation didn't immediately win everyone over. In its early days, the theory faced skepticism and scrutiny. Some scientists questioned whether such a rapid expansion was even possible, while others pointed out gaps in the model. For instance, Guth's original version of inflation had a problem. It predicted a universe that was far too lumpy, with regions of wildly varying density. This didn't match what we observe in the cosmos, where the distribution of matter is remarkably smooth on large scales. It was a challenge that could have derailed the entire idea, but instead it sparked a wave of innovation. Enter Andre Linde, Paul Steinhardt, and others who refined Guth's work and proposed new versions of inflation that solved these early problems. Linde's chaotic inflation model, for example, suggested that inflation could occur in different regions of space at different times, creating a patchwork of universes with varying properties. Steinhardt, meanwhile, introduced the concept of new inflation, which smoothed out the density variations and aligned the theory with observations. These refinements turned inflation from a bold hypothesis into a robust framework, one that could explain not just the Big Bang but also the universe's large-scale structure. The debates didn't stop there. Over the years, inflation has continued to evolve, with scientists proposing new models, testing predictions, and grappling with questions that push the boundaries of physics. For example, what triggered inflation in the first place, and how did it end? These are questions that still keep cosmologists up at night, driving new research and inspiring fresh ideas. Each milestone, from the detection of temperature variations in the cosmic microwave background to the ongoing search for primordial gravitational waves, has added another layer to the story, transforming inflation from a speculative concept into one of the most compelling explanations for the universe's origins. What's striking about this journey is how much it mirrors the scientific process itself. Inflation theory wasn't handed down from on high. It was built piece by piece through collaboration, competition, and the occasional stroke of genius. It's a reminder that science isn't just about answers, it's about the questions we ask, the debates we have, and the way we push each other to think bigger and dig deeper. And as we'll see next, this process isn't just about logic and equations, it's also driven by something far more human: imagination. Because when it comes to understanding the cosmos, sometimes the most important tool we have isn't a telescope or a supercomputer. It's the ability to dream, to wonder, and to imagine what might lie beyond the horizon of what we know. Imagination is the secret engine behind some of the most profound discoveries in cosmology. While we often think of science as a realm of cold, hard facts and rigorous equations, it's the spark of creativity that propels us forward. Take cosmic inflation, for example. This groundbreaking theory didn't emerge from a straightforward calculation, it was born from a bold leap of imagination. Alan Guth, the physicist who first proposed inflation, wasn't trying to solve the mystery of the universe's origins when he had his breakthrough. He was working on a problem in particle physics, exploring the behavior of hypothetical particles. But in a moment of insight, he saw how those ideas could explain the rapid expansion of the early universe. It was a classic example of thinking outside the box, of connecting dots that no one had thought to connect before. As Albert Einstein once said, imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world. This kind of creative thinking isn't just a luxury in science, it's a necessity. Cosmology, in particular, demands a willingness to dream big and ask questions that might seem impossible to answer. Thought experiments, for instance, have long been a tool for scientists to explore ideas that can't yet be tested in a lab. Einstein himself used thought experiments to develop his theory of relativity, imagining what it would be like to ride on a beam of light. In the same way, inflation theory began as a mental exercise, a way to reconcile the smoothness and flatness of the universe with the chaotic conditions of the Big Bang. It's a reminder that sometimes the most powerful tool in science isn't a telescope or a supercomputer, it's the human mind, daring to imagine what might lie beyond the known. But imagination alone isn't enough. It has to be paired with rigor, with the discipline to test ideas against evidence and refine them through debate. This balance between creativity and precision is what makes cosmology so exciting. As physicist Richard Feynman put it, science is imagination in a straitjacket. It's about dreaming freely, but also being willing to discard those dreams if they don't hold up to scrutiny. Inflation theory, for all its elegance, has faced its share of challenges and revisions. Yet it's precisely this process of questioning and refining that has made it one of the most robust explanations for the universe's origins. What's truly inspiring is how this interplay of imagination and evidence continues to drive discovery. From the earliest days of cosmology, when ancient stargazers mapped the heavens with nothing but their eyes and curiosity, to the cutting-edge experiments of today, the story of science is one of bold ideas meeting the test of reality. And as we'll see next, this journey of discovery isn't just about the universe's beginnings, it's also about how those beginnings shaped everything that came after, from the first stars to the galaxies we see today. Because while inflation might explain the universe's rapid expansion, it's the Big Bang that set the stage for the cosmos as we know it. Here's a fascinating twist. Cosmic inflation didn't just happen before the Big Bang, it set the stage for it. Think of it like a cosmic overture, a prelude that prepared the universe for its grand performance. During inflation, space expanded so rapidly that it smoothed out the universe, ironing out any wrinkles and setting the conditions for what would come next. But when inflation ended, it didn't just fade away quietly, it unleashed an incredible burst of energy, a cosmic finale that we now call the Big Bang. This wasn't just an explosion of matter and energy, it was the moment the universe as we know it truly began. Here's the kicker: inflation is what made the Big Bang possible. Without that rapid expansion, the universe would have been too chaotic, too uneven to form the galaxies, stars, and planets we see today. It's like inflation was the director, meticulously arranging the set before the actors, particles, radiation, and all the forces of nature took the stage. And when the curtain rose, the universe burst into existence, hot, dense, and ready to evolve into the cosmos we recognize. But how did inflation bridge the gap between the quantum world and the vast scales of general relativity? During those first moments, the universe was so small that quantum fluctuations, tiny ripples in space-time, played a critical role. As space expanded, these fluctuations were stretched, magnified, and frozen into the fabric of the universe. This created the seeds for everything we see today, from the smallest particles to the largest galaxies. It's as if the quantum world handed off a blueprint to the classical universe, ensuring that the Big Bang had the right conditions to unfold. The end of inflation marked a turning point, a moment when the universe shifted from rapid expansion to a slower, more measured growth. This transition released an enormous amount of energy, heating the universe to unimaginable temperatures and filling it with particles and radiation. It's like the universe took a deep breath after its explosive expansion and then exhaled, creating the hot, dense soup that would eventually cool and form atoms, stars, and galaxies. What's truly remarkable is how inflation connects two of the most fundamental theories in physics: quantum mechanics and general relativity. On the smallest scales, quantum fluctuations shaped the universe, while on the largest scales, general relativity governed its expansion. Inflation acts as the bridge between these two worlds, showing how the microscopic and the macroscopic are deeply intertwined. It's a reminder that the universe doesn't operate in isolated pieces, it's a seamless whole where every part influences the other. And as the universe continued to expand and cool, another mysterious force began to take hold: dark energy. While inflation set the stage for the Big Bang, dark energy is shaping the universe's future, driving its expansion in ways we're only beginning to understand. But that's a story for the next fact, where we'll explore how this enigmatic force is rewriting the rules of cosmic evolution. Now, let's turn our attention to a cosmic mystery that ties the past to the present: dark energy and inflation. At first glance, these two phenomena might seem entirely unrelated, one driving the universe's current expansion, the other responsible for its explosive beginning. But dig a little deeper, and you'll find they're more like cosmic cousins, sharing a family resemblance that could hold the key to understanding the universe's evolution. Dark energy, the mysterious force accelerating the universe's expansion today, behaves in a way that eerily echoes the Inflaten field, the energy behind cosmic inflation. Both are forms of energy that stretch space itself, but they operate on vastly different scales. During inflation, the Inflaten field caused space to expand exponentially in a fraction of a second, while dark energy is responsible for the slower, steady expansion we observe now. It's like comparing a sprint to a marathon. Both involve movement, but the pace and duration couldn't be more different. What's fascinating is how studying one could help us understand the other. The Inflaten field, while still theoretical, offers a framework for how energy can drive rapid expansion. Dark energy, on the other hand, is a tangible force we can measure, though its exact nature remains elusive. Could they be two sides of the same cosmic coin? Some scientists speculate that dark energy might be a remnant of the Inflaten field, a kind of echo from the universe's earliest moments. Others suggest they're entirely separate phenomena governed by different rules. Either way, unraveling the connection between them could shed light on some of the deepest questions in cosmology. Here's a thought-provoking question. If the universe underwent a rapid expansion once, could it happen again? Could dark energy in some distant future trigger another inflationary phase? It's a tantalizing idea, one that blurs the line between the universe's past and its future. While we don't yet have the answers, the parallels between inflation and dark energy remind us that the cosmos is full of patterns waiting to be deciphered. As we explore these connections, it's worth reflecting on how much we still have to learn. Dark energy, like the Inflaten field, challenges our understanding of physics, pushing us to rethink the fundamental forces that shape reality. And just as inflation left behind clues in the cosmic microwave background, dark energy is leaving its own imprint on the universe's structure, from the distribution of galaxies to the fate of the cosmos itself. But there's another layer to this story, one that takes us back to the very fabric of reality. If inflation and dark energy are cosmic cousins, what role does symmetry play in their behavior? This idea leads us to the next astonishing fact, where we'll explore how symmetry isn't just a mathematical concept, but a driving force behind the universe's most profound transformations. Now let's crack open one of the most fascinating ideas in cosmology: symmetry breaking. Imagine holding an egg in your hand. It's perfectly smooth, symmetrical, and uniform until you crack it open. Suddenly, the once perfect symmetry is broken and something entirely new emerges. This simple act mirrors what happened during cosmic inflation, when the universe underwent a series of transformations that shaped everything we see today. During the earliest moments of inflation, the universe was in a state of near-perfect symmetry. All the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces were unified, acting as one. But as the universe expanded and cooled, this symmetry began to break, much like the shell of an egg cracking under pressure. With each breaking of symmetry, the forces we recognize today began to emerge, separating into distinct entities. This process didn't just create the forces, it also gave rise to the particles that make up matter, setting the stage for the formation of stars, galaxies, and ultimately, us. Think of it like a cosmic recipe. The universe started with a single, unified ingredient, a primordial soup of energy and potential. But as it expanded, the ingredients began to separate, like oil and water in a salad dressing. Gravity peeled away first, followed by the strong nuclear force, then electromagnetism, and finally, the weak nuclear force. Each separation left behind a distinct flavor, a unique force that governs how matter interacts. Without this process, the universe would have remained a bland, featureless void, incapable of creating the rich tapestry of structures we see today. Why does this matter? Symmetry breaking isn't just a quirk of physics, it's the reason the universe has structure at all. It's what allowed particles to clump together, forming the seeds of galaxies and stars. It's the reason atoms can exist, and why you and I are here to ponder these questions. Without it, the universe would be a far less interesting place, a static sea of uniformity with no complexity or life. But here's the kicker: symmetry breaking wasn't a one-time event. It's an ongoing process, one that continues to shape the cosmos. Even today, as the universe expands and evolves, subtle shifts in symmetry are at work, influencing everything from the behavior of particles to the fate of galaxies. It's a reminder that the universe is never static, it's always changing, always becoming something new. As we marvel at the elegance of symmetry breaking, it's worth asking, was this process inevitable or was it shaped by chance? This question takes us to the heart of cosmic inflation, where randomness and probability play a surprising role. And that's where we're headed next, as we explore how the universe's most profound moments might have been guided by the roll of a cosmic dice. Now let's dive into one of the most fascinating twists in the story of cosmic inflation, the role of randomness. The universe we see today, with its galaxies, stars, and vast cosmic web, didn't form by design, it was shaped by chance. During inflation, tiny quantum fluctuations, random ripples in the fabric of space-time, acted like a cosmic roll of the dice, determining the distribution of matter for eons to come. Picture it like a lottery where every ticket represents a tiny region of space, and the winning numbers decide where galaxies will one day form. Some regions became slightly denser, others slightly less so, and these small differences grew into the structures we see today. It's a reminder that even in the grand scheme of the cosmos, randomness plays a starring role. What's remarkable is how these fluctuations, born from the quantum realm, became the seeds of everything we know. As the universe expanded, these tiny ripples were stretched and magnified, frozen into the fabric of space-time. Over billions of years, gravity took over, pulling matter together around these denser regions, forming the first stars and galaxies. It's like sprinkling seeds across a vast field. Some will grow into towering trees, while others remain small plants. In the same way, the universe's structure was shaped by the luck of the draw, a cosmic game of chance that left some regions rich with galaxies and others nearly empty. But these fluctuations weren't just random noise, they followed a specific pattern, a kind of cosmic blueprint that scientists have been able to decode. By studying the cosmic microwave background, we can see the faint imprints of these ancient ripples, like fingerprints left behind by the universe's earliest moments. This pattern isn't just a relic of the past, it's a map of how the universe evolved, a story written in light and matter. And while the fluctuations themselves were random, their consequences were anything but. They set the stage for the intricate web of galaxies and clusters we see today, a testament to how even the smallest acts of chance can shape the cosmos. This idea of cosmic randomness raises an intriguing question. If the universe's structure was determined by chance, what does that mean for us? Are we here because of a lucky roll of the dice, or is there something deeper at play? It's a question that blurs the line between science and philosophy, inviting us to reflect on our place in the grand scheme of things. But as we ponder these questions, there's another layer to the story of inflation that's equally mind-bending: the role of time itself. How did time behave during those first moments of rapid expansion? And what does it mean for our understanding of reality? That's where we're headed next as we explore the mysteries of time in the early universe. Now, let's take a moment to consider something truly mind-bending. What if time itself didn't always exist? What if it emerged during cosmic inflation, like a clock starting to tick only after the universe began its rapid expansion? This idea challenges not just how we think about the universe's origins, but the very nature of reality. Time, after all, feels like a constant, something that's always been there, always flowing forward. But in the strange world of quantum physics and cosmology, even time might have a beginning. During the earliest moments of inflation, the universe was so small and dense that the rules of classical physics break down. At these scales, time as we know it might not have been a well-defined concept. Instead, it could have been a kind of abstract, featureless backdrop, like a blank canvas waiting for its first stroke of paint. As inflation stretched space, it may have also unlocked time, giving it a direction and a flow. Imagine it like a river suddenly forming, carving its path through the landscape of the cosmos. This raises a profound question. If time began during inflation, what came before it? The answer might be that there was no before. Without time, there's no past, no future, just an eternal now. It's a concept that's hard to wrap our heads around, but it's one that pushes the boundaries of what we thought was possible. Could the universe have existed in a timeless state before inflation? And if so, what triggered the transition to a universe with time? These are the kinds of questions that keep cosmologists up at night, and they remind us just how mysterious the cosmos can be. What's even more fascinating is how this idea connects to our everyday experience of time. We think of it as a straight line moving inexorably from past to future. But in the quantum realm, time can behave in strange and unpredictable ways. During inflation, it's possible that time itself was stretched and warped just like space. This could mean that our perception of time as a constant, unchanging force is just an illusion, a byproduct of living in a universe that's already evolved past its earliest, most chaotic moments. As we ponder these ideas, it's worth reflecting on how much they change our understanding of existence. If time emerged during inflation, it means the universe didn't just create space and matter, it created the very framework in which events unfold. It's a reminder that the cosmos isn't just a place, it's a process constantly evolving and redefining itself. But as we'll see next, this process isn't just about time and space, it's also deeply tied to another fundamental concept, entropy, the measure of disorder in the universe. And that's where our journey takes us next, into the chaotic beginnings of a universe still finding its balance. Here's something that might sound counterintuitive. The early universe was remarkably organized. You'd expect chaos in the aftermath of the Big Bang, but instead the cosmos started in a state of incredibly low entropy, a term physicists use to describe disorder. Think of it like walking into a room that's perfectly tidy, with every book on the shelf and every sock in its drawer. It's not what you'd expect after a cosmic explosion, and yet that's exactly what we see when we look back at the universe's beginnings. This low entropy state is a puzzle, one that has puzzled scientists for decades. How did the universe start so orderly, and why has it been getting messier ever since? This is where cosmic inflation comes to the rescue. During that brief but explosive period of rapid expansion, the universe didn't just stretch, it smoothed itself out, like someone meticulously organizing a chaotic room. Inflation acted as a cosmic cleaning crew, ironing out wrinkles and creating a uniform, low-entropy state. Picture it like this. Imagine a cluttered desk with papers scattered everywhere. Now, imagine someone comes along and arranges everything into neat stacks, creating a sense of order. That's what inflation did for the universe, setting the stage for the Big Bang and the evolution of everything that followed. Without this process, the universe might have been a jumbled mess from the start, with no clear direction or structure. But why does this low entropy state matter? It's not just a quirk of the early universe, it's the reason time has a direction. The arrow of time, the idea that time flows from past to future, is deeply tied to entropy. As the universe evolves, entropy increases, and this increase gives time its forward momentum. Think of it like a deck of cards. When the deck is perfectly ordered, it's in a low entropy state. But as you shuffle the cards, they become more disordered and entropy rises. The universe works the same way, moving from order to chaos, and this journey is what gives us the past, present, and future. Inflation, by creating a low entropy starting point, set the stage for this cosmic progression. What's truly remarkable is how this solves one of the biggest puzzles in cosmology. Without inflation, explaining the universe's low entropy state would be like trying to explain why a deck of cards starts perfectly sorted. It just doesn't make sense. But with inflation, we have a clear, elegant explanation for why the universe began in such an orderly state. It's like finding the missing piece of a puzzle, one that not only explains the past but also shapes our understanding of time itself. As we marvel at this solution, it's worth asking, what powered this cosmic organization? What forces were at play during inflation that allowed the universe to start so smoothly? This question takes us to the heart of particle physics, where the building blocks of reality come into play. And that's where we're headed next, as we explore how the tiniest particles shape the universe's grandest moments. Now, let's zoom in on the microscopic world where the tiniest particles played a monumental role in shaping the cosmos. Particle physics and cosmic inflation are deeply intertwined, like two sides of the same coin. During inflation, the universe wasn't just a swirling sea of energy. It was also a playground for particles, fields, and forces that would ultimately define everything we see today. One of the most pivotal players in this story is the Higgs field, a kind of cosmic energy field that gives particles their mass. Without it, particles would zip around the universe at the speed of light, never clumping together to form atoms, stars, or galaxies. It's the Higgs field that allowed the universe to transition from a chaotic, high-energy state to one where structure could emerge. But the Higgs field is just one piece of the puzzle. During inflation, other quantum fields were also at work, each contributing to the universe's evolution in unique ways. For instance, the Inflaten field, the hypothetical energy field that drove inflation, interacted with these particles, stretching and magnifying tiny quantum fluctuations into the seeds of galaxies. It's like a cosmic orchestra where every particle and field plays a distinct note, creating a symphony that resonates across the cosmos. Even the tiniest fluctuations in these fields had profound effects, shaping the distribution of matter and energy on the largest scales. Here's where it gets even more fascinating. The behavior of particles during inflation wasn't just random. It followed specific rules dictated by quantum mechanics and the laws of physics. Take, for example, the process of pair production, where particles and their antiparticles pop into existence from pure energy. During inflation, this process happened on a cosmic scale, creating a universe teeming with particles. But as inflation ended and the universe cooled, many of these particles annihilated each other, leaving behind just enough matter to form the stars, planets, and galaxies we see today. It's a delicate balance, one that hinges on the precise interactions between particles and fields. What's truly remarkable is how these microscopic processes connect to the macroscopic universe. The same particles that danced in the early cosmos are the building blocks of everything around us, from the atoms in our bodies to the stars in the night sky. And while we can't see these particles directly, their effects are written across the universe, from the patterns in the cosmic microwave background to the distribution of galaxies. It's a reminder that the universe operates on every scale, from the infinitesimally small to the unimaginably large. But how do we piece together this intricate story? How do we go from theoretical models to a detailed understanding of how particles shape the universe? That's where simulations come in, powerful tools that allow us to recreate the conditions of the early cosmos and test our ideas. And that's where we're headed next, as we explore how scientists use cutting-edge technology to simulate inflation and uncover the secrets of the universe's beginnings. Simulations are the unsung heroes of modern cosmology, offering scientists a way to step into the past and witness the universe's earliest moments. Imagine trying to recreate the Big Bang in a lab. It's impossible. But with the power of supercomputers, researchers can simulate the conditions of cosmic inflation, testing theories and uncovering details that would otherwise remain hidden. These virtual universes aren't just tools, they're windows into the cosmos, allowing us to explore scenarios that stretch the limits of our imagination. One of the most remarkable examples is the work done by teams using advanced algorithms to model how quantum fluctuations during inflation grew into the vast cosmic structures we see today. These simulations start with tiny ripples in space-time, the kind of random fluctuations that might seem insignificant. But as the models run, those ripples are stretched and magnified by the rapid expansion of inflation, evolving into the seeds of galaxies and clusters. It's like watching a time lapse of the universe's birth compressed into mere seconds on a screen. The precision of these simulations is astounding. They can predict the distribution of matter in the cosmos with incredible accuracy, matching what we observe in the real universe. But these models aren't just about recreating what we already know, they're about pushing the boundaries of what's possible. By tweaking the parameters of inflation, scientists can explore alternative scenarios, asking what-if questions that challenge our understanding of the cosmos. What if inflation lasted longer? What if the Inflaten field had different properties? These simulations allow researchers to test ideas that can't be tested in any other way, offering insights into the fundamental forces that shaped reality. What makes these simulations so powerful is their ability to connect the microscopic and the macroscopic. They show how tiny quantum fluctuations, smaller than an atom, can grow into the largest structures in the universe, from galaxies to superclusters. It's a reminder that the cosmos operates on every scale, from the smallest particles to the vastness of space. And while we can't travel back in time to witness inflation firsthand, these virtual universes give us the next best thing, a chance to explore the origins of everything. As we marvel at the complexity of these simulations, it's worth asking, how do we know they're accurate? That's where observation comes in. The predictions made by these models are constantly tested against real-world data, from the cosmic microwave background to the distribution of galaxies. It's a dance between theory and evidence, one that pushes our understanding of the cosmos forward. And as we'll see next, the role of observation in cosmology is just as critical as the theories themselves, offering a way to ground our ideas in the reality of the universe we see around us. Now, let's shift our focus to something that ties all these cosmic theories together: observations. Without them, cosmology would be like trying to solve a puzzle with no picture to guide you. Observations are the backbone of our understanding, the concrete evidence that transforms bold ideas into scientific truths. From the faint glow of the cosmic microwave background to the intricate maps of galaxy distributions, every measurement we take is a piece of the puzzle, helping us test and refine theories like cosmic inflation. Take the cosmic microwave background, or CMB, for example. This ancient light, a relic from the universe's infancy, is one of the most powerful tools in a cosmologist's toolbox. By studying its subtle temperature variations, scientists have been able to confirm many of inflation's key predictions. These tiny fluctuations, some as small as 1 part in 100,000, are like cosmic breadcrumbs, leading us back to the universe's earliest moments. Without precise observations of the CMB, we'd be left guessing about inflation's role in shaping the cosmos. But the CMB isn't the only piece of evidence. Galaxy surveys, which map the distribution of matter across the universe, have also played a crucial role. These surveys reveal the large-scale structure of the cosmos' vast webs of galaxies and voids that stretch across billions of light years. These patterns aren't random, they're the fingerprints of inflation, the result of quantum fluctuations stretched to cosmic scales. By comparing these observations to theoretical models, scientists can test whether inflation's predictions hold up in the real universe. What makes these observations so powerful is their precision. Instruments like the Planck satellite and ground-based telescopes like the Sloan Digital Sky Survey have pushed the boundaries of what we can measure, capturing data with astonishing accuracy. It's like upgrading from a blurry photograph to a high-resolution image. The more detail we can see, the more we can learn. And with each new observation, we're not just confirming what we already know. We're uncovering new mysteries like the nature of dark energy or the distribution of dark matter. These discoveries don't just happen by accident, they're the result of meticulous planning, cutting-edge technology, and a relentless pursuit of accuracy. Take, for instance, the discovery of B-mode polarization in the CMB, a swirling pattern that could be evidence of primordial gravitational waves. Detecting this signal requires instruments cooled to just a fraction of a degree above absolute zero, placed in some of the most remote locations on Earth, like the South Pole. It's a testament to human ingenuity and the lengths we'll go to uncover the universe's secrets. But observations aren't just about confirming theories, they're about challenging them. Every new dataset has the potential to upend our understanding, forcing us to rethink what we thought we knew. This is the essence of science, a constant dialogue between theory and evidence, where each discovery leads to new questions and deeper insight. And speaking of new questions, what does the future hold for inflation research? As we'll see next, the next generation of telescopes and experiments promises to take our understanding to even greater heights, opening new windows into the cosmos and revealing secrets we can't yet imagine. But for now, let's take a moment to appreciate the incredible journey we've taken so far, from the tiniest quantum fluctuations to the vast expanse of the universe. Observations have brought us this far, and they'll continue to light the way as we explore the mysteries of cosmic inflation and beyond. As we look to the future of cosmic inflation research, one thing is clear: we're standing on the brink of discoveries that could redefine our understanding of the universe. The tools we have today, like the James Webb Space Telescope and ground-based observatories, are already pushing the boundaries of what we can see and measure. But the next generation of instruments promises to take us even further, opening windows into the cosmos that were previously unimaginable. Imagine telescopes so sensitive they can detect the faintest whispers of primordial gravitational waves, or detectors so precise they can map the cosmic microwave background with unprecedented detail. These aren't just dreams, they're the technologies currently being developed, and they're poised to revolutionize our understanding of inflation and the early universe. What makes this moment so exciting isn't just the technology, it's the questions we're asking. For instance, what exactly powered cosmic inflation? Was it the Inflaten field, as many theories suggest, or could there be other forces at play? And how did inflation end, transitioning into the Big Bang we know today? These are mysteries that have puzzled scientists for decades, but with new tools on the horizon, we're closer than ever to finding answers. Projects like the Simons Observatory and the proposed Light-Bird satellite are designed to probe these very questions, searching for subtle signals in the cosmic microwave background that could unlock the secrets of inflation. But the future of inflation research isn't just about answering old questions, it's about uncovering new ones. What if inflation wasn't a one-time event, but part of a larger cycle of cosmic expansion and contraction? Could there be other universes beyond our own, each with its own unique history and laws of physics? These are the kinds of questions that push the boundaries of science, challenging us to think bigger and dig deeper. And while they might seem like science fiction today, they could become the focus of serious scientific inquiry tomorrow. What's truly inspiring is how this research connects us to the universe's earliest moments. Every observation, every simulation, every new discovery brings us closer to understanding how everything began and where it might be headed. It's a reminder that science isn't just about finding answers. It's about exploring the unknown, embracing the mystery, and daring to imagine what might lie beyond the horizon of our knowledge. And as we stand on the cusp of these breakthroughs, it's worth reflecting on what they mean for us. How does understanding the universe's origins shape our sense of place within it? These are questions that bridge the gap between science and philosophy, inviting us to think not just about the cosmos, but about our role within it. And that's where we're headed next, as we explore the profound implications of cosmic inflation, not just for the universe, but for us. Now, let's take a step back and consider something truly profound. Cosmic inflation doesn't just explain the universe's origins, it challenges the very way we see reality itself. At its core, this theory forces us to rethink concepts we often take for granted, like space, time, and even existence. What does it mean for space to stretch faster than light? How can time itself emerge from a timeless state? These aren't just scientific questions, they're deeply philosophical, pushing us to question the nature of reality and our place within it. Take space, for example. We often think of it as a static backdrop, the stage on which the universe's drama unfolds. But inflation shows us that space is dynamic, capable of stretching, twisting, and expanding in ways that defy our everyday intuition. Imagine trying to explain this to someone centuries ago. It would have sounded like magic, yet here we are, using the language of mathematics and physics to describe a process that reshaped the entire cosmos. As physicist Brian Greene once said, "The universe is not what we thought it was, it's much more." Inflation reminds us that reality is far stranger and more beautiful than we ever imagined. Then there's time. We experience it as a steady, unbroken flow, but inflation suggests it might not have always been that way. During those first moments, time itself could have been fluid, even emergent, like a clock starting to tick only after the universe began its rapid expansion. This idea challenges the very notion of a beginning, suggesting that our universe might not have a single starting point, but instead emerged from a state beyond time as we know it. It's a concept that blurs the line between science and philosophy, inviting us to rethink what it means to exist. What's truly remarkable is how these ideas resonate beyond science, touching on questions that have occupied thinkers for millennia. Philosophers like Immanuel Kant argued that time and space are the frameworks through which we perceive reality. Inflation, in a way, takes this idea and turns it on its head, showing that these frameworks aren't fixed, they're shaped by the universe's history. Similarly, religious and spiritual traditions have long grappled with the nature of existence, often envisioning the cosmos as a dynamic, ever-changing entity. Inflation, while rooted in science, echoes these ancient ideas, offering a modern perspective on the timeless question of how everything began. But perhaps the most profound implication of inflation is what it tells us about our place in the universe. If the cosmos began as a microscopic speck and expanded into the vast expanse we see today, what does that mean for us? Are we merely cosmic dust, adrift in an indifferent universe, or is there something more to our existence? Inflation doesn't provide easy answers, but it invites us to reflect on these questions, to see ourselves as part of a story that stretches back to the universe's first moments. As Carl Sagan famously said, "We are a way for the cosmos to know itself." Inflation, in all its complexity, reminds us of that profound connection. As we wrap up this journey through cosmic inflation, it's worth reflecting on how much we've learned and how much remains a mystery. From the explosive expansion of space to the quantum ripples that shaped galaxies, inflation has given us a framework to understand the universe's beginnings. But it's also left us with questions that push the boundaries of science, philosophy, and even imagination. What powered inflation? What lies beyond our observable universe? These are the questions that will drive the next chapter of discovery, and they remind us that the cosmos is full of wonders waiting to be uncovered. So, as we close this exploration, let's take a moment to marvel at the universe's incredible story, one that began with a burst of energy and continues to unfold in ways we're only beginning to understand. Whether you're a seasoned cosmology enthusiast or just starting to explore these ideas, one thing is clear: the universe is a place of endless mystery and beauty, and inflation is just one chapter in its epic tale. And who knows, the next great discovery might be just around the corner, waiting to reshape how we see everything again. As we wrap up this incredible journey through the 28 astonishing facts about cosmic inflation, let's take a moment to reflect on what we've uncovered. From the explosive expansion of space faster than the speed of light to the quantum ripples that seeded galaxies, cosmic inflation has reshaped how we see the universe's origins. It's not just a theory, it's a story, one that connects the tiniest particles to the vastness of the cosmos, revealing how everything we know came to be. Think about it, in less than a blink of an eye, the universe went from a microscopic speck to a sprawling expanse, setting the stage for stars, galaxies, and ultimately us. Inflation smoothed out the cosmos, solved cosmic puzzles like the horizon and flatness problems, and left behind clues in the cosmic microwave background. It's a tale of symmetry breaking, random quantum fluctuations, and the delicate balance of forces that shaped reality itself. And while we've made incredible strides in understanding this process, the story is far from over. Mysteries like the Inflaten field, dark energy, and the multiverse continue to challenge and inspire us, reminding us that the universe is full of surprises. What's truly remarkable is how science has brought us this far. Through observations, simulations, and relentless curiosity, we've pieced together a narrative that stretches back to the universe's first moments. It's a testament to human ingenuity and our unyielding desire to understand the cosmos. As Carl Sagan once said, "Somewhere, something incredible is waiting to be known." And cosmic inflation is proof of that, a reminder that the universe is not just a place of wonder, but a puzzle we're constantly working to solve. But the journey doesn't end here. Every discovery opens new doors, inviting us to explore even deeper mysteries. What powered inflation? Are there other universes beyond our own? How did time itself emerge? These are the questions that drive science forward, and they're the same questions that invite you to keep exploring, keep questioning, and keep marveling at the beauty of the cosmos. So, what do you think? Did these facts about cosmic inflation change how you see the universe? Let us know in the comments. We'd love to hear your thoughts and questions. And if you enjoyed this journey through the cosmos, don't forget to subscribe for more mind-expanding content. The universe is vast, mysterious, and full of stories waiting to be told. Together, we'll keep exploring one discovery at a time. Thanks for joining us, and remember, the cosmos isn't just out there. It's a part of us, and we're a part of it. Until next time, keep looking up.